So, like always, I give you a user interface. And so assignment 4 is for you to write the back end of this genetic algorithm assignment. So the main part of assignment 4 is this Sudoku puzzle that we have here. And I guess before we get too much into the assignment, I believe Sudoku.com is still up, so I can go over the rules of Sudoku if you're not familiar with the rules of Sudoku. So Sudoku is a puzzle game. It's a single agent game. It's, if you want to list all the properties, it's fully observable, so there's no hidden information. And your job is to place numbers onto this grid of partially filled out numbers. So apologies to anyone who's done Sudoku before, but there's always a few people who haven't, so I'll just take a minute for this. So for example, in this relatively easy board over here, you've been given some of the grid cells filled out. And the point of Sudoku is that you are supposed to insert numbers such that each row, each column, and each of these smaller squares contain each of the numbers 1 through 9 exactly once. Okay? So for example, one of the strategies you would use for solving an actual Sudoku puzzle is to look for maybe the most completed cell that you have here. So for example, here we have the numbers 3, 4, 5, 6, 7, 8. And so I know that this number, and this number have to be a 1, a 2, or a 9, right? And so if I just do a little bit of logic here, this is a completely randomly generated puzzle, so I've never seen it before. So if I have a 1 or 2 or a 9, I know that this one can't be a 9 because there's a 9 right here, and that would create 2 9s in this row. Right here, this one can't be a 1 because then there will be 2 rows in this column, etc., etc. So you would go through placing numbers until you have solved the entire puzzle. So that's Sudoku. Very, very conceptually easy puzzle. For your assignment, you have not been given a partially filled out Sudoku. You're just using a genetic algorithm to try and generate a filled out Sudoku board. So if I go back here, this is a 9 by 9 Sudoku board. And your genetic algorithm is trying to come up with a Sudoku board which fits the constraints. Okay? So what you see here on the left-hand side, this is, or on the right-hand side first, the genetic algorithm is running. So as soon as you load the page, it starts running. And this is the solution code, so this is a working genetic algorithm. What you see over on the right-hand side is a plotting of fitnesses over time. So in the background, you're seeing this is doing approximately 100 generations a second. Actually, no, sorry. It's trying to do 1 generation per frame, and each frame it's a 60th of a second. So if your code is fast enough, this will be doing 60 generations per second. And over here, what we see is the blue line. That is the maximum fitness individual of any population. This is the average fitness of all the individuals in the population. And down here, this is the minimum fitness of any individual in the population. And so what you can see is over time, hopefully, this blue line keeps going up. And what you can see here is that I've gotten stuck in a local minima. Okay, so my board is not completely filled out. My fitness has sort of plateaued up here. And so let's talk about why that happens and what you have to do for the assignment. Also, over here on the left-hand side, we have a visualization of the actual Sudoku board. So what this is showing is for every population, every time the population is updated to the next population for the next generation, this is taking the maximum fitness individual of that population and just displaying it over here on the left. So if I reload this page, it starts out like really bad, and then over time, it starts to get better. So this is showing you the maximum fitness individual at any time. The coloring scheme works based on the rules of Sudoku. And the colors don't really matter. I've just displayed the colors here as a rough way of telling, like, quote unquote, how solved the Sudoku puzzle is. So if the cell in the Sudoku grid is white in the background, it means that there are no conflicts. And the conflicts are the 3 conflicts of a Sudoku board, right? So this 3 having a white background means that there are no 3s in the row, no other 3s in the row, no other 3s in the column, and no other 3s in this square. As you get more and more darker shades of red, there are either 1, 2, or 3 conflicts. So for example here, this 3, there's a conflict because there's 1 3 over here. This slightly darker shade of red means that there are 2 conflicts. So you'll see here there's a 4 in the same row, and there's a 4 in the same column. So that has 2 conflicts. And really quickly, if I go back to the start, then there's some really dark red ones that have all 3 conflicts. So by default, what you're seeing here is a Sudoku fitness function where you have essentially the inverse of the number of conflicts. Okay, so you take the number of conflicts and then you subtract from the maximum fitness function, which I believe is like 279 or something like that, and that's what you get. So a value of 0 would mean that everything on the board is in conflict, and the maximum possible 279 just means that there are no conflicts for anything on the board. Another way of looking at that is to say sum up all the unique values in each row, each column, and each square, and this value is the number of those unique values. Okay? So what you can see here is that the maximum fitness is obviously higher than the minimum fitness, and the average fitness is somewhere in between those two, which is completely what you'd expect from those values. And in order to play around with those values, let's have a look at the controls that we have down here in the bottom left. And I realize that this is a little small, maybe for those in the back to read, but I'll just go over with those with you here. So the first thing you have is this, it says a fitness function, and I'll get back to that. So I'll get back to that once I've explained the other controls. But for the Sudoku fitness function, you have this slider where you can create really big Sudoku puzzles if you want, or really small Sudoku puzzles. I don't suspect that you'll be solving completely without any conflicts the larger Sudoku puzzles. Even the 3x3 is like remarkably hard to solve, but you should be solving the 2x2 puzzle pretty easily. So you can see here that each of the rows, columns, and squares contains the values 1, 2, 3, and 4. But Sudoku was chosen intentionally as a problem that has many very troublesome local minima and maxima for you to fall into. So it's actually kind of hard for a genetic algorithm to completely solve it. The next thing down here is the population size. So right now, each generation, each population is of size 100. And if I come down here and increase this, this just increases the population size on the back end. That doesn't have any real noticeable effect other than we probably should be getting better results if we have a higher population size. But the downside of that is that each population will take longer because there's more individuals, right? Down here, this slider is the number of individuals that are mutated. And if we recall from the last time, what we're going to be doing for mutations in this assignment is just taking a Sudoku board and flipping a number to another random number. Okay, so that will help us to eventually generate a solved Sudoku board. The next one is the percent random genes inserted. So what this means, for example, if this is set to 5, that's a percentage. And if our population size is 100, then that means every new generation, one of the first things that we'll do is insert that many percent random genes. So if we have a 100 size population and 5% random genes inserted, then 5 of each of the population will actually just be randomly inserted genes. And what that does is it inserts a bunch of like random genes to keep the gene pool kind of fresh, to keep things mixing around, to make sure we're going to get better results. And the last one is called elite gene survival. And this, again, is a percentage. And what this means is every generation, you're going to take the top, if this is set to 10, the top 10% of genes that were in this generation, and then just copy them to the next generation. Okay? So the sum of this one and this one can never exceed 100. And if you see when I slide this, these sliders kind of change, so you can't actually insert more than 100. These are kind of locked in step. It took me like a surprisingly long amount of time to figure out how to do in JavaScript. But it works. So as a pop quiz, let me run this for a minute. This is a great exam question, by the way. So I'm gonna run this. Okay. What will happen to the average fitness if I increase the number of random genes that are inserted? Yeah, it'll probably go down. Why? Because random genes, if you randomly generate a Sudoku board, it probably has a very low fitness, right? So if you're inserting more things that have low fitnesses, then in real time, I just increase that to 30%, and you can see, okay, if 30% of the things are literally random, then the average fitness goes down. However, this fitness doesn't go down. Why doesn't that go down? Well, it will never go down because if I have an elite gene survival rate of greater than 0, then I'm at least taking the best one from each generation to put into the next one. So it can't possibly go down. But if I reduce this to 0, there is a likelihood that it'll go down. Why? Because if you do not specifically say, I want the best thing to always carry over to the next generation, then the probabilistic nature of selecting things to reproduce to the next generation does not guarantee that your highest, fittest individuals will continue on to the next generation. So if I do indeed put this down to 0, it's kind of wild, right? So it's not doing super well. This will increase over time, but there's no guarantee that my highest, fittest ones will survive. And if I put it up, then eventually you will see this climb. So it is kind of a good thing to keep those higher fittest individuals around. Now, as we explained in the notes, there are two things that we have to worry about with a genetic algorithm. One is the phenotype, and one is the genotype. So the phenotype is the actual representation of the thing in the real world, right? Like it's the muscular strength or whatever. So the phenotype here, that is the actual Sudoku board, the 9x9 grid of values that we are checking the Sudoku rules against. The other thing is the genotype. The genotype is the representation of the Sudoku board that we'll be using to do the calculations. And the genotype for the Sudoku board is just going to be a one-dimensional array. Okay, so this two-dimensional representation, the phenotype, is representing the one-dimensional array. And basically, all I've done is up here in the top left, this is the first thing in the 1D array. This is element 2, 3, 4, 5, 6, 7, 8, 9, and then 10, 11, 12, 13, 14, 15, 16. So I just take this row by row and unwrap it into a one-dimensional array. So that's already done for you. But just keep in mind that what you're going to be working with in the assignment when you're doing all your operators like crossover, mutation, etc., is the one-dimensional representation of that 2D Sudoku board. Now, I said down here that I have some different fitness functions. And this is really one of the really cool things about a genetic algorithm, is that you can write a single genetic algorithm and have it solve a multitude of different problems. Because the only thing that the genetic algorithm is really doing is trying to maximize the fitness of the population over time. So if I come down here and I change the fitness function, this one is going to be called sum values. So instead of trying to solve a Sudoku board, the fitness function for sum values is literally just take all the values in the grid and sum them up. And that's the fitness. So if I click sum values, then what you will see is over time, the numbers in the grid are just getting larger. So this is no longer like, I'm showing you on a Sudoku board because I didn't want to have different visualizations. But if what I'm trying to do is just maximize the sum of the values over time, then that's what this genetic algorithm, the same one that tried to solve a Sudoku board, is trying to solve this. Because all it knows is, hey, I'm trying to maximize the fitness. And you can see here that there's a couple of values that haven't quite changed yet, but it's probably because I'm not mutating enough of them. So if I increase the mutation rate, what we should see if I go back and increase the number of mutated things, oh sorry, this has it changed to some values, then this should climb and converge much faster than if we have lower mutation. And so the mutation rate kind of depends on the context of the problem that you're trying to solve, but you can see here that these are getting, we're almost there. Come on, you can do it. Just got to mutate that too. There we go. Okay, so I think we're at the maximum now. There's 1.8? Okay. Well, it's pretty good, right? Here, for example, there's another one that I wrote called match row. And so what this does, if it gives fitness if the number matches the number of the row that it's in. So we can see over time what's happening. Maybe I'll increase the population size here. Is that eventually we will have this gradient, and I'm just coloring things based on the number, but we get a higher fitness if the thing matches the row, and of course that 1,7 is just chilling out up there. Now, what I've done here, the fitness function, is not necessarily as good as it could be. Why? Because if you see here, the fitness up here is like 81, right? And all I'm doing is saying, okay, the fitness is the number of things that match. And so maybe there's a bug in my display, I'm not sure, but it says that the fitness is supposed to be maxed right now. So let me just run this again. Okay, but a completely solved grid has value 81, and if we're just one away, that has value 80. And so there's only like a 1.2% difference between those fitnesses, right? So if you are really trying to solve this, which is solved now, right? Anyone see anything out of place? Okay, we're good. All right, whatever. It's pretty much solved. But you can think of this as being, okay, do I really want to value an almost solved board as almost the same thing as a completely solved board? Like completely solved should be like this huge fitness value that we're trying to get to. And so sometimes it's not good to have these sort of linear fitness functions where almost solved is almost as good as being completely solved. Okay? And that happens for the Sudoku as well. This fitness value, you're saying, okay, if the maximum possible fitness is 279 or 281 or whatever that value is, if I'm, say, 5 values away from being solved, then that's like 275. So 275 versus 280, it's still only like a 1% difference. So if you wanted to do a more intelligent, like it's only, that almost solved board has only a 1% less chance of being chosen to reproduce than the completely solved board, right? So you may want to do something where you say, okay, completely solved things, the closer we get to completely solved, we're sort of ramping up the fitness function like quadratically or exponentially or something like that in order for it to have a much higher chance of being selected. As part of this assignment, you will be modifying the fitness function. And so just keep that in mind. Some more fitness functions that I have, okay, match column. This is just the opposite of match row, where eventually it'll be like 1 through 9 going across. And the bottom one here, I've assigned a point if it matches this like checkerboard pattern. And so eventually, hopefully, it starts to look like a checkerboard. And the algorithm hasn't changed. The only thing we've changed is the fitness function. And so the genetic algorithm is somehow able to work out all these different solutions to different problems just based on the fitness function, which I think is pretty neat. Okay, so I believe that is it for the demonstration. And all this stuff is done for you. You just have to write the back end, as I showed before. All right, so let's jump into the slides real quick. So what I've done for you in the assignment is, if PowerPoint wants to actually respond to me, I swear this laptop doesn't suck. Like, PowerPoint is fine. Oh dear. All right, well, we'll just go like this. So the step one of initializing a population with random individuals, I've done that for you. The code is in the GUI. I will show that later. It's like sample code if you want to know how to initialize individuals. This repeat until termination condition, that is done for you. So you can see on the page that new generations are constantly going. We don't really have a termination condition for this assignment. It's just going to keep running. And then the inside of this loop generates the next population from a given population. And this, steps 3 to 7, that is what you're going to be doing in the assignment. So I've provided you with a function. That function is called evolve. And you are going to do those step 3, 4, 5, 6, and 7 excuse me, inside that function. So let's hop over to the code. So again, there are many different files here in the assignment. There's the marking scheme, the solution, which I won't click on, the GA student class, that is where you will be writing all of your code. There is the GA GUI, that, again, that's just the GUI class. You don't need to look at that, similar to the GUI.js. There's the index.html. You don't need to worry about that. But there are 3 files that you need to probably have a look at. One is Sudoku.js. The other one is GAsettings.js. And then finally, we'll be looking at GA solution, or not GA solution, GA student.js. All right. So Sudoku.js, what is this file? I have written for you a Sudoku class, and it handles the majority of the annoying things about a Sudoku board. So what this does is you construct a Sudoku board with a given size, and that size is like, for example, 9. So if you pass in 9, it will be the 9 by 9 Sudoku board. Yes. Yes, okay, so you have to pass in a square. So 1, 2, 9, 16, whatever. So you pass that in, and then it has this variable called size, which is the size that it currently is storing. And then I have the square root size, so that is the square root of the size. So that's the size of the individual squares. So if you pass in 9 as the size, then the size of the squares, so this is the square size, is going to be 3 by 3. So I store that there. Then I have a board, and that board is just going to say, okay, for I equals 0 to I less than size times size, fill it up with zeros. Okay, so I am storing the Sudoku board internally as a one-dimensional array, and then when I draw it, I just draw it as a 2D array. If you pass, so there's a number of functions on this board that I've given for you, and you can look at this code and figure out what it's doing. But those functions are getIndex. So what this function does is you pass in a row and a column, and it returns for you the formula that I use. So for example, if you pass in row 2, column 1, then it will return the index of the 1D array representing that. So it's just like row times the width plus calls. And so I think that's the formula that's there. Yeah, so size times row plus column. That is to take a row and a column and get the one-dimensional index. So if you need that for whatever reason, that function is there. This is a randomize function. So this will just take the board and randomize it for a reason if you need that. This will set a value on the board. So it'll say, okay, the value at row column should be equal to this value. And so it looks up the index and sets that value. You may be interested in this one, which is get row column. So get row column is going to return the value of a specific row column on the board. Num conflicts, that is a function which you can use as part of your evaluation function. If you want, you can take this code, and it just looks over all of the rows and all of the columns and the square size by square size area and counts up all the conflicts. So this just says, hey, if we're in a row and this value is here more than once, that's a conflict. If it's in the same column, that's a conflict, and then it sums up all the conflicts. So that's the conflicts. And then this is just a helper function that I wrote that's for my purposes for the UI. It just takes in an array and it sets up a board And so what this does is it takes your genome and converts it into a Sudoku board. So this is the Sudoku class. I'm sure you'll be probably just calling the get row and column in order to implement your evaluation function. But that's it. That's what it is. It's stored as a 1D array, and it stores the Sudoku board. The next class that we should go over is called the GA settings class. And as you can probably imagine, this takes all the settings for the genetic algorithm. And there are a number of settings in a genetic algorithm, so we should probably store them pretty neatly. So the constructor for the GA settings takes in, right now, a Sudoku size. So if you were writing this for a different problem, you'd probably have a different constructor, but we're talking about Sudoku puzzles, and so our settings rely on this Sudoku size. So the constructor, it has a number of variables in the settings, and so when you have your evolve function, you're going to be passed in a settings object, and so you can get all of these variables from the settings object. And what happens is the user interface, as you modify those variables with the sliders, it modifies the settings in real time, and then that's passed into the function for you. So you don't need to worry about what's happening in the UI. You just get given this really neat settings function, and then you can say, okay, there's the elitism ratio, there's the population size, so I'll construct my next population based on these things. So the first thing that we have here is the fitness function. And believe it or not, in JavaScript and many other languages, you can just store a function as a variable. And so what we can do here is, based on that selector in the UI, whenever I select a different fitness function, it just changes the fitness function in here. And so what you can do in your code is just apply the fitness function variable as a function to your gene, and it will carry out that the fitness function on your gene. So basically, all that is done for you by the fact that we can store a function as a variable. The next one is the individual size. So what individual size means is our genotype is going to be an array of integers. And because this is an evolutionary algorithm with an array of integers as its representation, that makes this a genetic algorithm, right from the slides. And so a genetic algorithm needs a genotype, which is basically just an array of integers. And so if we pass in a Sudoku size of 9, for example, then our individual size is going to be 81, right? Because it's 81 different things on the Sudoku board. And then here I have some default settings. But of course, you're going to make your code work based on those variables. So whatever I set the settings to, your GA should still work. So this is the population size. That is going to be, okay, if this has changed, then your next population is going to have that many things in it. The elitism ratio, this is represented from 0 to 1. So all these rates here, these are 0 to 1. So 0.1 means 10%, 0.2 means 20%, 0.05 means 5%. So this would mean, okay, a mutation rate of 0.2. How would I mutate my thing? Well, I have a 20% chance of mutating every child. And so what happens is I'm going to generate a random number between 0 and 1. And if that is less than this, then that role has succeeded. Therefore, I will mutate that thing. So that's how that works. The random ratio, very similar. That's the number of random things you pass in. So for example, at any time you are given a ratio and a population size. So if I want to know what is the number of elite things that I should carry over, well, you're going to take settings.elitism ratio and multiply it by settings.population size, and that is the number of things that I should copy from this to the next thing. If I similarly have a random ratio, then I multiply random ratio by population size, and that's the number of random things that I'm going to insert into the next population. Down here, this last thing that I have, this is called individual values. And what this array is, it's a little helper array, and what it says is these are the possible values that I can have in any index of my array in my current game or my current environment. So what this says is, okay, from 1 up until Sudoku size, individual values .push I. So what this means is that a legal possible value for any of the things in my Sudoku array is between 1 and the Sudoku size, right? So for example, you shouldn't bother with inserting 12s into a 9 by 9 Sudoku because it's not a legal thing. So if you ever want to, say, get a random legal value when you're doing your mutation, you can use this individual values thing. And in fact, I have actually used that here to create a function for you. So I've done so much of this assignment for you. I should, probably have you do more, but whatever. This is an algorithms class, not an implementation class. So here, what happens is, in order to get a random gene value, so let's say you have a child and you want to mutate that child. And so you're going to pick a random place in that child to be mutated, and you want to say what should go there. Well, I want a random legal gene value to put there. So what this does is it says, okay, I have this individual values array, which stores the values that are legal, and I want to take a random one of them. So I'm going to take a math.random. So math.random in JavaScript generates a number between 0 and 1. I multiply that by individuals.length, and then I convert it to an integer by just taking the floor of that value. And then I use that as the index into here. So if this array stores all the legal possible things, if I pick a random thing from that array, then that is going to be a random legal value for this gene. And so you can just call this function whenever you want to get a random legal value for your thing. Down here, these are all of the fitness functions that I use to do those other fitnesses. So for example, the sum fitness function, that's really easy. I just literally go through everything in the array. So this gets passed in an array, which is the gene. It goes through, sums everything up, and then returns the sum. Similarly, I have the checker fitness function, the match row fitness function, and the match column fitness function. I don't need to go over those. You can have a look if you want. But essentially, it just says, hey, go over everything. If it's the same as the row or it's the same as the column, increase the fitness by 1 and return that. It's a really easy fitness function. So that's the GA settings class. Genetic algorithms do have a lot of parameters, and so whenever you're writing one, you want to make sure that you have a class that handles all of those settings nicely so that they're easily modifiable, they're easily readable. If you have like a text file, you're writing this in C++ because you want it to be super fast. You could have like an experiment file, a text file with all of these things in it that you could change from one experiment to the next, etc. Just good programming practice to keep all this stuff together. So that is the GA settings class. And the final one that we will look at is the GA student class. And so again, you're used to this by now. This is where all of your code will live for the assignment. So the very first thing that I'll talk about is this very important note up here. It's that I said that theoretically, a population is a population of genotypes, right? So if you think of a population as an array, then a population should be an array of arrays. And those arrays are the individuals, and all of their values are stored in there. However, for convenience's sake, what I've done for this assignment is instead of an individual just being an array, an individual is actually a JavaScript object which contains 2 values. One is gene, and what this is, that is the one-dimensional genotype representation. So the array is object.gene, and then the second thing is the object.fitness. And .fitness, that is the fitness of the individual. So rather than, like in the roulette wheel selection pseudocode that I gave you, instead of having a population over here and another array of fitnesses over here, where index i's individual matches index i's fitness, what I've done is just sort of combine them into one thing. So an individual is a gene, and then we've evaluated the fitness of that gene and just stored the fitness with it. So if you want to do something, for example, like sort the population by fitness, it's very easy to do if you have it stored in this way. But if you had them stored in separate arrays, then you'd have to do like co-sorting of 2 arrays, and it's just super annoying. So wherever you have, you're iterating through a population, and you are currently looking at element I, so population I, that is this object where you have a gene, which is an array of integer values representing the genotype, and then the fitness, which is a number representing the fitness. So just keep that in mind while you're doing the assignment. Okay, so the very first function, and where most of the functions are, so all of the other functions that you have to do are just helper functions to help you do this function. And so this, I have numbered it out from 1 to 5 of all the things that you have to do, so it is very well spelled out in these comments exactly what you have to do for your assignment. And this GA-evolve function, again, is just literally what is between 3 and 7 here. So you evaluate the population, you select the parents. I still have no idea what's going on here. Let me just try and fix this, because I'm going to want to change the slides at some point. Hang on. I think the issue is I'm using Google Drive, and I don't have it downloaded, so it's like streaming the PowerPoint or something from my Google Drive. It's probably not a great idea. All right, where was that slide? Okay, so here is what goes in that GA-evolve function, everything from 3 to 7. So let's go back, and we'll have a look. So the GA-evolve function takes in 2 parameters. One is population. That is the previous population. We are trying to evolve the next generation, a new population, from this input population. The second variable is the settings. And so if you want to know what the settings are, just go back into the GA-settings.js, and then that is the settings object that you're passed in. And again, the UI updates all of those things in real time, and so you don't want to like store the settings somewhere, because every time this function is called, the settings may have changed, and they're reflected in this settings object. So the very first thing that you have to do is set up a new array which will hold the next population. Okay, so that is literally just, here, I have it for you. Let next population equal empty array. And so your job is to just fill it with the correct stuff. So the very first thing to do, it is not necessary to do this, but because of the operations which we will be doing, I think it is very helpful to, the first thing you do, sort the population descending based on fitness. So there is a bunch of sorting functions that are in JavaScript. Like you can just say whatever array.sort this value based on its fitness, and it'll just sort it descending for you. You've got to do something on the assignment, so I'm going to leave that part up to you. You could write bubble sort or merge sort or whatever you want to do, but I highly recommend the first thing you do is take the population that was passed in and then sort that descending based on fitness, which means that the very first thing in the population is the highest valued fitness individual, and then it goes down from there. Once you have that, it'll make some things, like this next step, much easier. So the next thing that you do is take the top N elite, meaning the top fitness individuals, and put them into the next population. The percentage of elite genes to carry over is given in settings.elitism ratio. Sorting the population array by fitness is an easy way to do this. So what you'll do is you'll just say for let I equals 0. And now how many do I want to actually carry over? Well, that's just settings.elitism ratio times settings.population size, I++. And now if this is properly sorted from, I've got a missing semicolon here, so it's, there we go. If I see red squiggles, I can't move on with it. I just got to fix it. So this is what you would do. And then you would take the highest individual and copy it over to the next population, then the second one, and then the third one, etc., until you get to this one. And all you need to do is, take population I and push it into next population, and then it'll add it to the end of that. That's it. So that's that part. Super easy if you have your array sorted. Next, add the number of required random individuals to the next population. The percentage of random genes to carry over is given in settings.random ratio. So again, what you'll do here is you'll create a for loop, and you'll loop over from I equals 0 to settings.random ratio times settings.population size. Okay? Now, keep in mind that you're not using this population size. You are using the settings population size because in the UI, you can change the slider, right? And so if the slider is changing, let's say we've gone from 100 to 500, but you're not using the new size, then if you just keep using the population's length, that's the previous population, so it'll just stay the same size no matter what. So just make sure you're using settings.population size instead of population.length. So the only tricky thing here is to actually construct the new random gene. And so you can get a random gene value by calling settings.getRandomGeneValue. That's already done for you. And make sure you add the following object to the array whenever adding an individual, right? So I've given you the code for it here. So nextPopulation.push gene, and then gene variable, and then fitness settings.fitnessFunction gene variable. So the only thing that I haven't done for you here is create gene variable, all right? So what you have to do to create this gene variable is you create a new array, and then inside settings.individual size, for I equals 0 up to individual size, you're going to add a random gene value into that array. So if it's size 81, you're going to create this array of 81 random gene values. Then you take that variable that you created, you stick it inside this object in its gene variable. Then you call settings.fitnessFunction on that gene variable, and that's the object that you create, and you just push that new one into the next population. Okay? So you can literally do this. That is done for you, and then all you have to do is generate that gene variable. So let gene variable equal whatever, add the new random stuff to it, and then this is the calling of the fitness function is also done for you, right? So that just calls the fitness function for you. Next is where sort of the meat of this algorithm comes in, and this is the parent selection, the crossover to create the children, and the mutating of the children, okay? So perform child generation process, which is as follows. So keep in mind, up until this point, let's say you have a population size of 100, you have an elitism ratio of 0.1, and you have a random ratio of 0.05. So if you have 10% of the population carried over from the previous, with a population of size 100, that's 10 individuals, then you inserted 5% or 5 random individuals. So what you have now is you have a new population with 15 things in it. And so what you have to do is, okay, there's 15 things, but I need 100 things. So the remaining 85 things that you have to put into the population come from this part. Okay, and that's the generation of new children. So what does this look? So we keep adding children until we fill the new population. First, compute the sum of all the fitnesses in the population. So let's go back to the slides. The roulette wheel selection algorithm that we looked at last time, that is the algorithm that we are going to be using in this assignment. So here is the algorithm for that. And as part of this algorithm, we have to compute the sum. And so what the sum is you just go through the entire population and you sum up its fitness and you store that value. And that's just part of, where is it? Yeah. Then you pick a value and it's between 0 and sum. That's why you need that sum. So every time you compute this, you're going to have to compute this sum. So what we do here in the assignment is so we're going to be needing this sum in 2 different places. So rather than computing it twice, I'm just computing it once and then passing it in. So what happens is there is a roulette wheel selection function, which is right here. And so you are going to write this function. So you get passed in the population. So that is the previous population that you're selecting parents from, and a fitness sum. And basically all you do is you come over here and you copy and paste this pseudocode and turn it into JavaScript. Okay, so that's what you would do there. So this function, pretty easy algorithm. You should have no problems with that. And so you're doing that for parent 1, and you're doing it for parent 2. And because it's a randomized process, it's very likely that you're going to be selecting 2 different parents, and then, okay, now we have 2 different parents. These parents are individuals, right? So they have a gene and a fitness. And now what you have to do is you have to take those 2 parents and create 2 children from those 2 parents, all right? So that is where the crossover function comes in. And crossover is here. So here, for example, if we're doing crossover, we are taking 2 parents. So we have the first parent in green, the second parent in red. You are just cutting these down the middle. So you find the middle index. So if this is an even length array, the middle is pretty easy. If it's an odd length array, then you just choose like 1 to the left or 1 to the right of the middle, right? Because there's like 1 value in the middle. You can't cut half an array index. And then you're going to create 2 new children based on this, all right? So you're going to cross over and create this child, and then cross over in the other direction and create this child, just this child. So crossover, what that does is you're going to create a child gene, okay? So that is the gene that you're going to create. You're going to add the first half of parent 1 into child gene, and the second half of parent 2 into child gene. And that should be the same length as the parent, right? You should not change the length. So if you had 81 going into this and you have 82 coming out, you know you did something wrong. And so just note that the size of the child gene must be the same size as the parent gene. Be very careful when the parent is odd size and there's not an exact half. Choose 1 or left to the right of the midpoint. It doesn't really matter. And then what you do is once you have the child gene, this part is done for you. This returns that child with the fitness function evaluated. So you don't need to change this. This is done for you. All you have to do is create that child gene. So what happens is we take parent 1 and parent 2 and create a child with the first half of parent 1 and the second half of parent 2, and then we call it again, but the parents are swapped. So we take the first half of parent 2 and the second half of parent 1 for the second one. Then we call the mutate individual function. And so this mutate individual function is down here. And what this does is, based on the individual and the settings, it changes a random index of the gene to a random gene value. So one time it may change the second number to a 7 from a 2. The other time it may change the 31st number from a 3 to a 4 or whatever. You just choose a random index between 0 and the length of the gene to mutate, and then you give it a random value. And so the mutation chance is if a random number between 0 and 1 is less than the mutation rate. So what that means is that if you want to, and this is what you would do in most of programming, most programming languages have a way for you to generate random numbers, right? So if I give you the setting value, which is settings.mutation_rate right here, if that's 0.1, that represents a 10% chance. So the way that I recommend to do this is to generate using math.random. That'll give you a number between 0 and 1. And if that random number between 0 and 1 is less than 0.1, well, there was a 10% chance of that happening, right? So that's why we've represented the number these ways. So if math.random is less than settings.mutation_rate, yes, I will mutate this thing. Otherwise, do not mutate that thing, because we're saying that, hey, 10% of individuals should be mutated. And so that's why we're doing that. And so this modifies the individual and returns nothing. So because this is JavaScript and this is an object, it is passed by reference. And so if we modify this individual here, it will be modified in the function that was calling it. And so all we do is we look up the gene, the random index that we've generated, change it to a random value, and that's it. I don't need to return anything in this function. So then we have mutated child 1 or child 2, or both, and then we add the children to the population. But be careful not to add child 2 if it would go above the population size. What do I mean by that? Well, I've shown you in this example that up until we started generating children, we had 15 of 100 things already inserted, right? So if we insert 2 children, 2 children, 2 children, 2 children, Well, we have an odd number, we're adding even numbers, so eventually we'll land on 101 things in the population, but we don't want that. So just make sure that you're checking, okay, add child 1, but only add child 2 if the population size of the next population size is less than settings.population size. So just make sure that you're not accidentally adding an extra individual because of the parity difference. And so the next population array should always be the same length as settings.population size. And then, of course, down here, make sure that you're actually returning the correct thing. Just so the UI works, when I give you the assignment, I'm returning population, but that's the previous population. Make sure that you change this to next population when you actually do your assignment. And the very last thing that you have to do for this assignment is at the very bottom here. So this is the Sudoku fitness function that I've given you. And I want this to be a little bit more clever, okay? So if anyone in the class can get your GA, let's say within a minute or two, actually solving the 9 by 9 Sudoku, I don't think anyone's ever done that in the history of the class, because it's just a hard problem. So if you don't completely solve the Sudoku, it's fine, it's expected. But you will find that if you modify this fitness function to be a little bit more clever, you can get far closer to a solved Sudoku than what I have, right? And again, just to go over, and so all this code is here, you can modify this code if you want, but you should, A, significantly change it so that it's doing something new, and B, document in the comments here what it is doing. Because it's such a array-heavy calculation that it's not always obvious what it is that you're trying to accomplish just by looking at the code. So make sure in English you just describe, here's what we're trying to do. Like for example, I'm saying add the unique values in each row, add the unique values in each column, add unique values in each square. That's fine. If you do something else like, hey, take these values and take the log of those values because we think that'll create a bigger difference between different fitnesses or whatever, that's actually opposite of what's true. Log would shrink the differences rather than grow them. But if you use another operator, let me know why, right? Like what is the reason that you did? And again, if I come back here, the reason this fitness function sort of accomplishes its goal, but not really, is again, let's say that the maximum fitness function is 280 or whatever it is. I want to reiterate this because it's very important. That 280 of a solved board is very not different from the 279 of an almost solved board, or maybe this is what? This is 224. What's the difference between 224 and 280? So that's 56. 56 divided by this, that's 20% or less, right? So there's less than a 20% difference between this monstrosity and an actually solved board. So what you can do to change the fitnesses is try and scale it, for example, so that as you get closer to being solved, the fitnesses become much higher, right? So I don't even want to look at a 150 fitness board, right? 150 fitness is randomized. So this means that a randomly generated garbage Sudoku board has only half the chance of one of these almost solved Sudoku boards, more than half the chance. Ideally, I don't even want to be considering those. That should be a 1% chance. So what can you do to the numbers to make it so that Sudoku boards have an exponentially higher chance of being selected for parents if the fitness function, or if they're closer to being solved? So that's what I want you to do. Just think about that. How can you change the numbers? And you change them to whatever you want, because the only thing that matters is how unread this board gets, right? So try and change the fitness function for that. And one last thing I forgot to show you in the code is in the GA GUI. If I scroll down here, this bit of code here, starting at line 38 or around there, It's going to be different in yours because you have your header info inserted. So this might be like line 50 or something. This is the code for setting up a random population. So in here, I have actually done part of the assignment for you, and I don't want you to feel guilty or sleazy for like looking at that. So you can completely look at that and use that code as part of your assignment if you want. And what this does is it sets up a whole new population of random individuals, and you can kind of take that and modify it in a specific way to do the insertion of the random genes for your actual, for your assignment code. And just let me make sure that there's nothing else that I'm missing here. Oh yeah, let me go over the marks. So, because the Sudoku is so difficult to actually solve, what we'll be doing when we mark your assignment is I'll be setting this to 2. And if within 30 seconds or so, it doesn't solve 2, and we'll try it a few times. Come on. It should solve 2. Oh yeah, it should solve 2 because your fitness function is going to be better, right? So it should solve 2, no problem. It should get to the point where the vast majority of these are white, okay, so that you're getting closer to a solved board. However, we're also going to be checking these other ones. And because these are convex problems that have no local minima, only a single global maxima, then your code should be doing what my code is doing here, right? So we should be getting very close to a solution very quickly. If it doesn't get that last one, that's fine. But all of these, it should be working for all of them, okay? So that's really the way that you judge if your algorithm is working. So if you want to know, okay, is my GA, is the algorithm actually working? Is it evolving? I would suggest using these as a test rather than the Sudoku one as a test. Hey, guys. Talk after class. So let's just go over the marks. Of course, you have this 5% nitpicky code style readability stuff. Next is 30% for the GA functionality. So it solves the 2x2 easily. It makes progress toward the 3x3. Sorry, 3x3 meaning 9x9. It solves all of the non-Sudoku fitnesses for 9x9. So that means that those other fitness functions, it gets close to solving those. The graph of fitness over time makes intuitive sense. So your graphs should look like this. Okay, there should be a maximum clearly defined, a minimum which is fairly stable, and then an average in between them. And then the individual functions and the actual operation of the GA make up most of the marks. But keep in mind that, for example, if mutation isn't done, sure, you lose 5% for the mutation, but if mutation doesn't work, none of this is going to work, right? So it's not just the individual function, the whole thing has to work as well, right? But I don't think many people will have a real problem with this. The marking scheme is pretty well set out. And down here, the 10% of the assignment is for the improvements to the fitness function. So make sure you actually do something and try and be clever there.